Okay, so we're gonna go over quiz number 6, and I'm gonna go ahead and share. Okay, let me see, minimize this one out the way. Okay, so quiz number 6. Okay, so quiz number 6. Pretty much most of this is mainly basic concept from the LabVolt, and it's also from Mr. Pham handout too. So for number 1, they want the AC voltage gain in CC circuit. So so in CC, so you're going to gain, your gain is going to be less than 1. So your voltage gain is going to be V out over V in. So your V out is going to be at the emitter, and then your in is at the base. And since we know that VE is always going to be less, it's going to be VB minus the 0.7. So therefore VE is always going to be less than VB. So therefore the gain would be always going to be less than 1. Okay. So the answer is C, as in cat, for number 1. Okay. Number 2, the collector voltage of a CE transistor circuit equals that is going to be just equal to the power supply. So therefore, it's going to be coming in like this one right here. Oops. Yeah, let me see. So this is common collector. So common collectors is going to be your power supply. It's actually your input voltage. Okay. And so that's what it is. So that's the same thing as VA in this label. Let me see back into, okay, so. So the answer is C, as in cat, for number 2. Okay, number 3, the common collector transistor circuit exhibit. Okay, so this is the characteristic of a common collector amplifier. Okay. So the only one, so this is so exhibit high. The only thing that's shown that exhibit high is the high input impedance. Pretty much the whatever comes in goes out. So therefore your voltage gain stays stable or stay consistent. There's no gain there's no gain, and so the only one that you have that's high input is the impedance. So the answer is B, as in Bob, for number 3. So any question on number 1, 2, or 3? Okay, no question. Next page. Okay, so the AC output signal of a common collector circuit is mainly it's in phase with the output. So as you can see right here, the input, you put in a small sine wave, and you get output. It's also the same sine wave. It's in phase. So the answer is C, as in cat, for number 4. Number 5, the transistor DC operating conditions are referred to as the transistor bias. That is you applying the DC right here. Depending on where you apply your DC, you can apply at the collector, or you can apply at the emitters, or you can but pretty much, you know, most of the time you see it's going to be this voltage divider, like Mr. Pham mentioned before. That is the most that you will see most often. So your DC power supply is to bias the transistor to make sure that your resistor is working correctly. Okay, so the answer is A, as in apple, for number 5. Number 6, the transistor bias determine it determined all this. So everything in pink here: saturation, the Q point, as well as the cutoff. So the answer is D, as in David, for number 6. So any question number 4, 5, or 6? Okay, no question. Next set. Okay, so number 7, the transistor bias determined D. That was the same question as the one before. So the answer is D, all the above. So like I said, saturation, Q point, and the cutoff. So A, B, C are correct. So the answer D, all the above. D as in David for number 7. Number 8, when the transistor.
Number 6 was D as well.
Yeah, number 6 is also D. Yes, that's the same thing. All the above is it. Okay. And this one would be the same thing as all the above. Okay, so number 8, when the transistor temperature increases, what happened to your beta? Okay, so your beta would increase because you're going to have, you're going to be, as the temperature increases, you're going to have the increase in your output current. And so your beta is going to be, your beta is IC over your IB. So therefore, you're going to have a lot more current over the collector. And therefore, you're going to have an increase in beta. So increase in temperature, you're going to have an increase in beta. Okay, so that's number 8. So B as in Bob as for number 8. Number 9, the collector current of transistor and voltage divider bias circuit with emitter resistor is almost independent of changes in mainly beta, because you look at this one is they're talking about the emitter resistor. Okay, and beta only determine IC over IB. It doesn't have anything to do with the emitter resistor. It does affect with the collector resistor as well as the base resistor, but has nothing with the emitter resistor. Okay, so the answer is the C as in cat for number 9. So any question number 7, 8, or 9?
A general question for 8.
Okay.
Does when the transistor temperature increases?
Yes.
For beta?
Mm-hmm.
My question is for environment. I'm assuming that any component that surrounds the transistor is going to influence the transistor's current, which is understood. Is it known to have any other cooling device, even though a transistor is very small, placed on top of a transistor or around it to keep the current at a stable rate when the component temperatures around it fluctuate? Is that a known possibility for keeping a controlled current, to have like say an aluminum heat deflection or some type of not necessarily a fan, but is there a technique to keep a transistor cool for a stable current?
Pretty much you look at most of your transistor that you're going to be, anything that's going to be amplifying your output, you're going to have to put a heat shield to draw out the additional heat from the transistor.
Thank you.
Okay, you're welcome. Okay, any other question? Number 7, 8, or 9? Okay, no question. Next set. Okay, the RC circuit. So RC is stand for resistant and C is for capacitant. So the answer is D as in David for number 10. Okay. So number 11, the output signal of a common emitter 2-stage RC coupled amplifier is. So number 11, the answer is A as in Adam for number 11. So this is what you will see. Okay. So you got your first stage that will be going, so your input is going toward your base, and then it's going to be going amplify output on your at your collector. This is what you have as your first stage. And then after that, this first stage would be feeding into the base of the second stage amplifier, and the output would come out on the collector, and then so now this is 180 degree. Now in the second stage at the output, it would flip again. So you have a gain, but you're going to be at the same phase as your input signal. Okay, so this one is going to be in the same phase as the input as the output. Okay, so that's why the answer is A as in Adam for number 11. Okay, number 12, let me go ahead and shrink down this a little bit. So maybe it's way to the bottom. Okay. Okay, so let me see. Number 12, each stage of a common emitter 2-stage RC coupled amplifier produce 180-degree phase shift between the input and output signal. Okay, so that's what we see. You got this one right here. You got so this one, and then you got output that's 180 degree. And then after that, it could feed into the input into the second stage, and then it flip again to so whatever was in the negative now become positive. Whatever was in positive now it's become negative. So the second stage output would be this one right here. So that's what produces 180-degree phase shift between the input and output signal. Okay.
Now, Sam,
Yes.
with the two stages you connected with the RC, does that actually changes the phase?
No, because you're gonna be feeding here. So you're gonna take this. You're gonna have this transit. Okay, so you got resistor number 2, 3 here, but you just ignore this load here. Just take this whole transistor, put it over here.
Right, but then
Okay.
usually on the RC circuit, doesn't it the phase changes?
No,
Yeah, like I said, it does. Okay, the first stage. So the first stage is already changes from here. It flipped 180 degree, and then after that, this would feed into the next stage, and then it would flip again to the signal would get flipped 180 degree again, and so
Right,
therefore now the output matches what the input.
Right. No, I mean.
but yeah, but the question is, RC is not change the phase.
It does not, like when we it's always saying currently the voltage or vice versa in RC or RCL circuit. That's got nothing to do with that then.
Right,
Yeah,
that's
this-
just a capacitor at the collector, just a blocking DC.
Okay.
Yes. Yeah, this one that doesn't do any filtering.
Okay. All right. Thank you.
You're welcome. Okay, so number that's 10, 11, and 12. Okay, any question on 10, 11, and 12? All right, everybody's good. Next set. Okay, so the voltage drop across a Zener diode in normal use. Okay, so normal use, we look at pretty much that stays constant. I don't have the that signal before, but yeah, pretty much stays constant. That's just the same thing as what the voltage drop over that, say that over any set diode, that just at 0.7 no matter what. Okay, so that pretty much the voltage drop across over is going to be pretty much stays constant. There's no change.
Isn't that the same as answer C? It's either
Yeah,
0.3
yeah,
or 0.7.
answers C, but most of the Zener diode, like we said, it's working reverse bias. This one, depending on you using germanium or silicon. So yeah, but mainly it's going to stay constant. Even if you use the 0.3, it still stays constant, or 0.7 stays constant. But the one that would I think this one would answer more correctly, because it doesn't matter which one you use, it's going to be always going to stay constant.
Okay, about number 13, they're talking about Zener diode in normally yield. That means normally they break it down. Okay, so when they break it down, then they have to be remain constant. Whatever wanted on the Zener.
Input. Yeah, doesn't matter how much you put into your input, the Zener. If a Zener output is supposed to be 12 volt, it will stay at 12 volt all the time. Doesn't matter you increase it to 15 volt, 20 volt, 30 volt. When it's breakdown, it's going to stay at 12 volt as the output. So therefore you have constant output.
Okay, thanks. I just wasn't sure what normal use meant, if that was forward biasing or reverse biasing breakdown.
That
Yes.
normally yield, if they say just a diode, that means either 0.7 or 0.3, depend. However, now they say Zener diode.
Yes.
What you want to use for Zener, you want it to be breakdown. Okay,
12 volts, something.
so you have to understand when they say normal yield, that means they normal breakdown.
Okay. All right, number 14, a transistor have a VCE of 8 volt and a collector current of 4 amp, okay? Must be able to dissipate about 32 watts. So that just follow the power law or power rule, okay? So power is equal current times voltage. So you got 4 amps as your current times 8 volt. That's about 32 watt. So the answer is B as in Bob for number 14. Number 15, if the diode in a half-wave rectifier circuit is reversed, the polarity of the DC output is reversed. This is directly from the homework question, okay? So any question on number 13, 14, or 15? Okay, no question. Next set. Okay, the emitter of a PNP transistor is identified on schematic symbol by, okay, so this is your NPN right here. So you got your arrow is pointing toward the emitter. So an arrow is pointing away from the base. So therefore, here's the base. Here's the arrows that pointing away from the base. Okay, so the answer is B as in Bob for number 16. Number 17, the transformers are used in a power supply to convert line voltage to a proper level required by application, depending on what appliance you're using in your home. That's how you use the transformer to convert it accordingly. And same thing with your laptop and your computer. They have that transformer built inside that would able to convert your whatever the voltage that is coming from the outside of your home into your computers, that they're going to be converted to your computer power supply. Okay, so that's number 17. So the answer is A as in Adam. Number 18, if the additional base current is applied to a saturated transistor, okay, so the collector current will remain unchanged, okay? So it doesn't matter, once it hits saturation, doesn't matter, there's nothing going to change your current. That is the maximum current possible at your collector current. Okay, there's no matter what, there's not going to be any more than that. All right. So any question on number 16, 17, or 18?
Sam, on 18.
Yes.
You got IB, no, each one you have IB equal to 0, you go to 1, 2, or whatever, keep going up.
Yes.
And saturation is when it's at the max, is that what it is? Right?
Yeah, your IC would be at the maximum. Your IC that going through your collector would be at maximum. So it remain unchanged no matter what.
So in other words, that curve or that graph cannot go any higher. That's maxed out.
Yeah, this one they're showing is a picture of IB here. That's the curve going here.
Okay.
Okay, but your saturation is right here at this point at here. Saturation, it'll from here to this point, it's only minus small bit, but it's consistently at this point, it's at your maximum point possible.
Okay.
Okay. All right, so that's okay, so that's pretty much it. Okay, so I know that look like the transistor giving a lot of people trouble. I know from the transistor transistor, since the quiz number 5 and 6 seem like everyone seemed to have so much trouble with this transistor. So make sure you guys spend some more time studying this. So like I said, if you have this question, just go through your notes, and if you have question, bring up to Mr. Pham. He'll able to clarify it, because transistor is essential that you're going to be using on like all the circuit. So it's always come down to the transistor. All right. So, yes, go ahead, Lo.
Technical question. I can kind of understand it myself, but maybe I just need a little clarification. So at saturation, full voltage, full amplitude, the transistor is working at its peak for current flow and voltage per the manufacturer, correct? So
okay, so
at saturation, the highest voltage level has been attained and the highest current level has been attained, correct?
Yeah, the maximum amount of current, yes.
Right. So let's say that your temperature around transistor starts to increase, will that amplitude level also increase? At what point where will the transistor just not allow anything to affect it, where there will be a higher uncontrolled current flow or voltage? Can the transistor technically work like a fuse and burn itself out, or will it just keep maxing out and just pop off the board, you know, if it gets fried? What's a scenario that would happen if you understand what I'm saying? Where the heat surrounding it increases and the voltage and the current over
Yes.
peaks, I guess you say, goes further than what it's designed for. It should, in a sense, just fry itself out, right? Disconnect.
What do you think,
Okay,
Mr. Pham?
okay. Now, you understand the IC equal beta times IB, correct?
Listening, correct. Yeah.
Okay. Now, when you can using that formula, only thing is when you say the transistor in the amplifier, not cut off, not saturation, right? If you say the transistor is saturated, you cannot using that formula. Is it correct or not?
So basically what you're saying, whatever's requirement downstream, it will only take what is required. So even if it increases by the
Right,
heat-
right,
right.
right. I agree. However, what I'm saying is you have to agree with me. If the transistor, you get the formula IC equal beta times IB, that only apply when the transistor is the amplifier. Is it correct?
Based off of your explanation.
And if the transistor cut off, you cannot using that formula to calculate the IC, correct?
It sounds correct.
Yeah, same thing. If they saturated,
Right, right.
then you cannot using that formula.
Yeah, like we're saying, once it hits saturation, that is the maximum current possible. And then if you want it to operate like a switch, it either operate in the saturation or in the cutoff. But if you want to use it as an amplifier, it has to be in the on, yeah, when it's forward bias. So therefore, that's the only time that you can use as an amplifier. Other time it can use as a switch, which is saturation or at cutoff.
Right, understanding it. Just it's a question of whether at what point it's going to say, look, I've had enough, I can't work anymore because of a heat situation. That's kind
Now
of
that's a different story.
right. All right, thank you.
Okay, so back to you, Mr. Pham. Thank you.
Thank you, Sam.
You're welcome.
Can I interject to ask a question? It's on the transistors and the homework. On some of the assignments, you were supposed to put a transistor in the MSIM lab.
Mm-hmm.
It calls for a specific beta, but there's a lot of different transistors in there.
Oh, yes.
It doesn't clarify which ones and how to select the beta. It looks like you can change the beta, but
Okay, what assignment are you working on?
I think it's 16 and 17.
Okay, 16 and 17. Yeah, because it's not stated on the schematic. Okay, let me go ahead and pull up 16 and 17 just so that way you can see.
It's helpful to test so that you start looking at a lot of these things. So
right, so
it's helpful to know which ones to use. So
right. Yeah, only that I can tell you is by try and error. So you said 16 and 7, 6 and 7, or
16 and 17.
16 and 17. Okay, 16 and 17. So 16. This is the one that I used. Let me see. Maximize it. Okay, so I use the 2N3702. that gave me enough of the beta because it's not stated on the assignment. So yeah, so I had to interpret that.
Okay, thanks.
Yes, and then on the 17, open up, open 17, 17. So 17, I use, so in 17, I just use the virtual one.
Sam, what made you, what made you, what in your mind made you select certain transistors?
I just try it out. If it doesn't make it past, I choose the next transistor
Okay, so
and go through the process of measuring it. Because sometimes they're not going to tell you which one it is, and they just tell you to collect the data for them. And so therefore, you look at whatever's on your virtual, just put it on there and collect the data and label it, so that way you know which transistor or which transistor you're applying.
okay, mainly you're just saying trial and error.
That's as a technician life. Sorry, there's no shortcut to it.
No, that's cool. That's cool. That's cool.
Yes.
Okay, I guess I'm not sure what you mean by trial and error, because there are specific answers based on the beta will change, which will change the answers, but we don't have the answers.
But
right?
what do you,
Right. Like I said, because I put it onto the assignment, and then if it doesn't pass, then I go ahead and sort of delete this transistor and then just look at the next transistor. So click on there, click on the transistor listing. Let me see where is my list. So I pull up the next list here and then just look at the NPN. So NPN, so I look at the transistor here, look at for NPN. So here's a couple, so I just go down through the list. Usually the normal that we learned this one is just the first one. So usually we choose the first two because you go into the process of learning. But if you're working out there in the field, yeah, the engineer, whoever designed it, would tell you which one it is that you're using. And sometimes if you're working with a real circuit and it's got burned out, so it's completely gone. So therefore, now you have to go through and look at the blueprint, like Mr. Pham said, you have to look at the TRD, to tell you what is needed, and so you can build and test it on your simulation. And then if that fit with your circuit, then that's most likely the parts that you need. Okay.
Great. Okay, thanks, Sam. That's helpful. Appreciate
Okay,
it.
you saw the handout for number 16 to see what the transistor.
Homework. Okay, homework. Assignment 16. Okay, assignment 16. Okay. And then enable editing. Okay, so this is assignment 16. It didn't show. As you can see, you just showing the NPN, but doesn't tell which one it is.
Is it the simulation?
Yeah, this is a simulation. This is assignment 16. So if I open up, so I sit there and try it with different things until I get the right one, which is the one that actually works is with this.
What the beta equal?
It doesn't say on this one.
Didn't say.
you don't have the nomenclature of the transistor nor the beta there. So the info isn't there, Mr. Pham.
Yeah, so on the assignment, it doesn't state, and so it's really hard to tell which one it is and or whatever the transistor number.
Okay.
Yes. So therefore, I keep on trying for different one until I get the right one, and until I get the assignment to pass. And then once I get the pass, then I'm assuming that's the one that you did the test on.
Okay.
So you're going to update, Mr. Pham?
Yeah, I will be looking to that.
Yeah, just watch this video right here. So that is it. Yeah, just watch the video. It's right here. Okay. All right. Back to you, Ms. Pham. Thank you.
Thank you, Mr. Sam.
You're welcome.
Okay, make sure everyone know. Next week will be no class, holiday. take a whole week. And after that, you get only 3 more weeks. And we hit into the another 2 weeks off for Christmas. So we almost will be close to end of the fall 2021. Okay, now the lecture, I believe we can be done. Not a problem. However, the lab, that's really a problem. So normally, I will be show you how to do the lab vault. The thing is, a lot of circuit board we have to do. In the lab vault, you don't have to go one by one, step by step, to read it, to answer the question, multiple choice A, B, C, D, okay, or true or false. A, B, C, D, you pick A, they not pass, you pick B, or C or D, they will be pass. I think we have to get through that quickly. Otherwise, it takes you about 2 years to do the lab vault in order to get it done. Okay, so we don't care about that. On up the multiple choice. Just quickly select to pass it. Only thing we want, you have to do the lab. That means the lab, we need to get it done quickly. Okay, if you don't have any problem, you're using the meter, using the oscilloscope or generator, then follow the step by step, what they're telling you. First thing, they show you the circuitry they want to build. They want to connect. And now you have to make sure you get the right connection. Then they apply the signal and they measure the output. Okay. If they measure the output, it's wrong, incorrect. If we cannot get the right output, then you cannot moving on. Okay. In that situation, what you need to do, make sure the input apply is correct. Make sure the circuitry correct as they want you to build. And if you couldn't find anything, what can you do? You see everything you did look like it's okay, but how come you cannot get the correct answer? So who knows what you think you can do?
Maybe you need to evaluate your equipment.
Now, I already said they're not correct answer. They can be caused by your test equipment.
That's
Okay?
what I said. That's what I said. You got to evaluate your equipment.
Put the wrong board in.
You have to make sure you get the right input. Second thing, make sure your circuitry built the way they want, correct? And also you already check that and you say, okay, look like nothing wrong. Then what can you do to solve the problem?
You ask
Try
the,
to get don't try to get the answer from someone else to answer to let it pass.
Mhm.
you actually ask the help.
Exactly. That means you need the lab instructor to come up helping you. Okay, if I'm doing it, first thing I commit, I want to make sure your circuitry will correct like they want. Okay. Then I make sure that the input signal is okay. And I make sure you measure the output, equipment will be okay. And now everything look like to be it's okay. Then I will be tell, okay, now we need another board, okay, to replace that board. Make the same connection to see if we can get the correct answer. Now, if we get the correct answer, that means the board you're working on is not lucky. That means there really is something wrong in that circuit. Then what lab instructor will be doing? They have to take the note, okay, on that board, and later on, they have to fix it. If you want to do a job, that's okay. We will be let you do it. That means what? That means I allow you to open that board and replay the part. We get everything for your guy to do it. After you replay that part you think it's wrong, then you can test again. If it's part, that means you do a correct one. That's a real work. Okay. But if you get the time, we get everything in order you're able to fix it. That normally circuit board have to fix by the lab instructor or by myself. Okay.
So if you can fix that board from the lab vault, Mr. Pham,
Yeah,
then that person is a real technician, right?
right. That's what I have to fix it. I can get the part from the old circuit board, say we're not using anymore. We remove the part from that and replace for this board and try to test again. That's what normally we have to work it. Not guarantee the circuitry 100% working.
Mr. Pham, question?
Yeah,
I remember when we were doing lab votes, there was other help functions on the display screen, like a little video icon or a little help icon or a little internet icon. And sometimes the video allowed a little pop-up instruction, or some of the other icons, there would pop up another written description or typed out description as far as help. I was just wanting to make sure that was mentioned, whether or not you want that as part of your help. You know, in case you're busy and you have 5 students that need help, isn't on the lab vault. There's those other help options, right? So I think one of them is internet, and it links automatically to the internet and tries to help you find a question, but I think it's not exact as far as the link to try and answer the question. So that might be something that I know when I was doing the level, that was a problem that popped up for me. I tried to use the software to answer the question while the instructor was busy. All right, that's all I want to say. Thank you.
other thing that normally you don't have to spend too much time for that thing. Either at work or in the level. Okay, let me go back to the level last week. Now I can get a much better to set up my equipment. Okay, let's see. I will be talk a little more about what you're talking about. Can you see the circuit?
No, you didn't share the screen.
Okay, sorry. I have to share the screen.
We only see you, Mr. Pham. And you look the same. You never get old.
Okay, now you can see.
Yes.
Yes.
Let's see, I have to make sure that circuitry will be more clear. Let's see. Oh, we need to turn off the light. Okay, now it looks better, right?
Um, yeah.
Okay, so that one they said to connect oscilloscope channel 1. Okay, to that point here. And that will be the route. Okay. That's what I connect. Okay, scope channel, a generator here. You see that? That's a generator. And the scope channel 1 go to generator also. And the scope channel 2 at this point. Okay. And this circuitry connecting, they're not telling you any wanted anything. Okay. Now, the next connection on to probe, we already did it. So that is what they want. They want generator 20 volt, 100 hertz. Okay. On the scope channel 2. They want here 20. So now we go into the scope. Let's see. Okay, so they want to connect on that channel 2 into here. Okay, so connect channel 2 to the secondary. Okay, and this is a route for channel 2 oscilloscope. And now they say observe the transformer primary, secondary in phase. And if you're looking into the scope, and that's why you can see both going up, both going down, that's in phase. So now, if they're not in phase, or you cannot see anything on the channel 2, then what happened? What can we do? That's a very simple thing. My question, if you're looking at the channel 2, they're supposed to get signal like we show you on the oscilloscope. They will be in phase. That the frequency supposed to be 100 hertz. I just changed it to the 100 hertz. Okay. Okay, so they will be in phase. If they're not in phase, or they not show up any sideways on the channel 2, what do you think you can do?
It's obviously a drop down.
Check your wiring. Where
It's
you
your
connect
circuit.
to. Yeah,
Check your wiring, connect your circuit, right?
yes.
Okay, that means, let's say in here. Make sure you have to get the 2 pole. One connect here, one connect here, and one connect to R1 here. Okay, you see that okay? Look like it's okay. So now if you didn't see the signal on the channel 2, my question is, what do you think you can do to solve the problem? That's a very simple thing.
To make sure you get the right signal, the correct signal.
But you're not.
Right, but you have to understand the transformer is it from 1 to 5 ratio? And if you understand your ratio, then you can,
Oh, no, I don't care about that.
but you can interpret your signal on the oscilloscope then if you know your ratio.
But the thing is right now, they supposed to be show your signal on channel 2, but you didn't see it. I just asking you, in that case, now, how can you do it?
You need to check the the cord or the probe that goes from the scope to your circuit to make sure it's making proper connection.
Okay. That means right now you see the signal on channel 1, right?
Right,
However, you do not see on the channel 2.
right.
So the first thing is you have to make sure your scope channel 2 is working.
Correct.
How?
Put channel 2 to channel 1. The contact, the jack, put it where channel 1 is, and make sure you get the identical signal first.
That's exactly. To make sure channel 2 working on your scope, you just connect channel 2 also to channel 1. And they're supposed to be displayed both signal identical. Then you don't have any problem with the scope channel 2.
Hey, Mr. Pham,
Yeah,
another way of saying that is, okay, your channel 1 is working. So if you take the probe from channel 2 and put it on channel 1 and it doesn't work, then that would show that the one on 2 was defective. Is that the same thing?
that means if you connect the scope channel 2 to the channel 1, you didn't see the signal. You get a problem with set up your scope channel 2.
Right, right.
Then that's how you can check it out to see why.
Because you know channel 1 works, but now once you switched up, you know channel 2 must be defective because the channel 1 was working, correct?
Exactly. That's the easy way to guarantee scope channel 2 working. Okay.
All right.
Now, if you scope channel 2 working, but you didn't see signal, only thing is you need the lab instructor. They take it, the wiring, everything okay, they change another board. Okay. And if that board working, so they're telling you the transformer on the one not working, is something wrong. Okay. That's it. And now that the transformer step up and down. So you're looking on the scope channel 1, what the voltage, and the scope channel 2, what the voltage. Okay. And if I'm looking into that, right now you can see scope channel 1, how many volt? 20. Okay. Scope channel 2, 24.4 volt. So they will be up or down.
Down 1-to-5 ratio.
The question is they want to know, is it a transformer step up or step down? Which one?
Channel 1 is the primary or secondary?
Okay, channel 1 connect to the primary.
Okay.
Channel 2 connect to the secondary.
Okay, then step up.
Step up, correct. Okay, now you connect it where? Connect the scope channel 2 to positive and negative of R1. Okay, so you can move channel 2 positive and channel 2 round into negative. Okay, and then you can see the signal. Will be look like.
Full-wave rectifier.
Right, exactly. Full wave rectifier. Okay. that will be both alternation will be rectified yet. Okay, so now they want to get the frequency of the output. What frequency you get? Shannon Joe.
200 hertz.
Exactly. The thing is, input here will be 100 hertz. Output will be double. Okay, 200 hertz. So now, if you cannot get that output here, okay, either, you cannot get the full wave rectifier. Then what you think got the problem?
One of the diode.
That is the one of the answer. What else?
Part of the coil's burnt.
Make sure you understand. We don't have to deal with the wiring, okay? If you cannot get the full wave rectified, so as I showed you, one student said caught by one of the diode can get the problem. Okay, I agree. I want to know anything else can got the problem.
The resistor is open.
Exactly. Maybe the resistor is open. Okay, now in the left volt, then you cannot do anything. Only thing that you need the inductor coming up, okay, to help you. However, I'm talking about the real work in the company. In the company, you're doing the same thing. And now you make the output, they're supposed to be full wave rectified, but you cannot get that full wave rectified. My question is, what can we do now to fix it? That means I want to get a minimum thing before you can give it a ball for assembler people to fix for you. However, before you let them know which caused the problem, you have to get a minimum thing you must be doing. So in here, you can say either diode problem or either resistor problem. So what do you think you can do?
Check the forward bias of each diode with the DM and check the resistance of the resistor.
How do you check the diode?
Well, the DM puts out a specific voltage that will measure the forward bias. The
Okay.
DM
Now, at work, then you must be turn off the power. Right? You cannot check the diode with the power on or resistor. So you must be turn off the power for the circuit. Then you can using the meter to check the diode one by one to see which one wrong. Using the meter, then you can connect the positive in the anode and negative cathode here, measure the resistance, and you revert that measure. And the ratio between resistance forward and reverse, they have to be different about 100 times. That diode, okay. Otherwise, diode get a problem. That's an easy way to do.
Mr. Pham, so you don't disconnect the diodes, right?
You cannot disconnect the diode. At work, you cannot do anything. You see that? You cannot leave the diode. No. You cannot do anything with the circuit board.
Okay, then explain one more time, explain how you check the resistor and the diode.
Okay, you take the diode. If you remember on the diode, okay, you can connect the high side meter, low side meter, set diode to measure resistance, okay? Try to see how much resistance you get. Then you reverse your meter, high side on the other one, low side here,
Mhm.
and measure again to see how much resistance you get. The difference have to be over 100 times. Then the diode, okay. That means you measure between the
The anode and the cathode.
right, but measure with the on and with the off. Then resistance have to be quite different. Then the diode good. If it's not, that diode got a problem. And you have to do 4 times. Make sure the diode, okay,
So you check all 4 diodes.
right. After that one, you say, okay, next one, next one, next one. And now, the last one, you take the resistor. You can put the meter one side, the other side, measure ohm. Make sure you get right or close to the value. If open, that means you need to, you can see, you can give it a circuit board to assembler. You ask for, I want to change the R1. And they did it for you.
Question, Mr. Pham?
Go ahead.
In the case that a DM is malfunctioning, let's say just scenario, the DM is malfunctioning, your cables don't work, you don't have a backup multimeter, and you need to get the work done. The only thing that you have left over is an oscilloscope. So for each diode, you take your channel probe and you go to each diode and see if there's a signal. Now, for each diode, would there be the same signal as displayed on the oscilloscope? And if there wasn't that same signal on the oscilloscope, all right, if that signal wasn't there,
Okay, I understand what you say.
right? So
That means you get signal on the out secondary. Then you can check it right at this point. But the thing is, right at this point, you don't have it. You see that?
your ground difference will be different though, right? For each diode, you literally have to move the ground to.
No, the thing is you have to get the right connection. They're already telling you how to make the connection. You
Right.
connect on the positive scope here and negative have to be here, not here.
No, I understand, but let's say, can you use the oscilloscope as a DM and connect, test each diode to see if you have the same signal? And if you
Okay,
don't,
I understand.
if you don't, what would the signal look like? Would it be just a straight line?
Yeah, I think you say you connect the scope probe oscilloscope channel to one in here and another in here, right?
Yeah, anode, cathode, credit, yes.
You want to take only one scope, one diode here. But I guarantee you get nothing. The thing is right now you see nothing. How come you can do that again? You already get nothing when you connect this way. Okay. In some different circuitry, we can troubleshoot that way. But on this one, it's so easy. You measure right at this point, and at this point, you get no signal. Then I can guarantee most of the time, the diode can cause the problem.
So if a technician is not understanding the circuit correctly and they don't have the equipment just because there's a equipment failure or whatever, the oscilloscope in this situation can't be a backup. So you pretty much have to find another DM is basically what it gets down to. So my question just applies to try to get the work done, what equipment is available and what type of situation might occur. So the oscilloscope, like you say, isn't going to assist appropriately as to what the digital multimeter will in completing the full test for the diodes and the resistor. Thank you.
Okay, normally, technician at work, you get everything need to do your job. Okay, so we're not supposed to be in that situation. Only thing I want to tell you, in this circuitry, when I measure this way, I cannot get the output. First thing I can tell you, diode can cause the problem, not a resistor. The reason is, okay, the reason is diode will be active component. You understand what they mean, active component? Like transistor, like amplifier, they are active component. Why?
Nie możesz sam zaciszyć. Starasz o sobie.
Why I can say the diode active component, transistor active component, op-amp is active.
Is turning on and off.
They need the power, right? Without the power, transistor not working. Without the signal, then diode is not working. So whenever they need the power and the signal, that's what they call active. More likely they will be failed. Resistor will be inactive. So resistor is really very hard to be backward. Okay, that's what you must be know. Okay, so now you measure in here, and
Mr. Pham, can I have one last question?
yeah,
My question, Mr. Pham, remember how we said we check all the diodes with the probe at the plus on one end, plus on one end, I don't know, feedback, plus on one end, minus on the other, and then you switch it around, you check all four, and then you check the resistor. The resistance that you get at R1, what is the relationship to those diodes that you check? Is it opposed to?
no, they let you know. 47 ohms, for example. You must get the value.
Can you mute somebody's mic? Somebody's
Let's say I mute the mic. Okay.
all right, Mr. Pham. So you're saying if R1 is 47, I don't know, ohms?
We don't care. You're supposed to be no.
Okay, all right. All right,
When you test it.
okay, thank you, thank you.
Nothing will be unknown in here, okay?
Okay, thank you.
So now, if they pass it, then measure the V. Let's see. I don't care what they say, set channel, vertical, sensitivity, whatever. We don't care. We're using the digital scope. They want to measure peak DC output voltage. What do you think you're supposed to get? Even I don't have to measure, I still know what the value is supposed to be. Now this signal already show you here. Okay. And they want the peak voltage. This is the signal. And they want the peak voltage. Peak voltage will be measured from 0 up to the top. What do you think the quick one is the right answer? Who knows?
Ask the question again, Mr. Frank.
You say you're reading here. They say measure the peak DC output voltage.
From the oscilloscope, your peak to peak is channel to peak is 11.6. But peak to peak is actually your peak value. So the output, the answer should be 11.6.
Okay, now input you get a 20 volt peak to peak. So the peak will be 10, right? For your signal input.
Yes.
Okay, so when they rectify it, and that the diode will be turned on. So you can get a DC for the diode, minus 0.6 or 0.7. So the peak normally you get a 10 volt, and now basically they will be going little low to a minus 0.6 or minus 0.7. So the top, the peak will be measured from a 0 up to the top. I believe you can take 10 minus 0.6 or 0.7, and you can get around 9.3, 9.4.
Hey, Mr. Pham, since you got these waveforms up here, can you demonstrate that with your marker and your pen or something?
Okay, now if you're looking on that one here, that's a rectifier, right?
Correct.
Okay, input in here. Okay.
Right.
20 volt peak to peak.
Right.
So V peak on the input will be 10.
Right.
So this guy is supposed to be 10. Same thing like peak on the in. Correct?
Okay, on that bottom one, say that again. That from that top.
On the top in here, okay, you get a V peak to peak 20 volt. So V peak only 10. Correct?
Yeah, we got that part, Mr. Pham. We're talking about the bottom.
That they rectify. Okay, they rectify only peak. Okay, so they're telling you the voltage from 0 up to here. That's a V peak at the output, right?
For the rectifier.
Right.
And on your scope says that it's 11.6.
Okay, 11.6, I don't care on that. Okay, that depend on when you try to do, you have to set your oscilloscope to DC coupling or AC coupling. However, if you're looking on the signal here, from my understand, when you get the output, the diode have to be on. If you're looking on the schematic here, this diode on, right?
Right.
When they on, then the output will get a negative minus 0.6 or 0.7, correct?
Correct.
So on this one, showing here, okay, they go a little down here. That means going a little down to the minus 0.6. However, when you measure the V peak, you have to be from the 0 to the top. So that's why you have to get the peak normally will be 10. However, they going a little down for 0.6 volt negative. So you have to measure from 0 to the peak, you get around 9.4. Maybe you enter 11.6. No, I don't think so. Okay. You're working on, you can see. And if you want it, okay, then you have to spend more time to try to display on the scoping here. Let's see if we can. I try to see coupling, see any difference. But the thing is, this is so easy, so that's why I'm not doing. I press channel 2. Right now, coupling AC. I can to DC. Okay, then auto set and measure. And now you can see they can start from DC right here. That's a 0 here. Okay, so if you want it, you can using the cursor to measure. Press the cursor and cursor channel 2. Okay, and type I want voltage. Okay, then I move the cursor. That's on the top. Okay, and the second on the bottom here. Have to be a leader. Okay, so basically delta equal 10. That means they not get the signal basically going leader down to minus 0.6. Okay, however, if you enter 10, they still pass. Okay.
Is this a step up transistor? Is the input 20, step up to 25.6?
24.
24, so it should be 24 cut in half minus 1.4, 1.2.
Why 1.4? Only 0.6.
You got two diodes.
Only one diode.
Two diodes.
No, only one. Right here, right? And that two diodes on, right? So basically positive, this diode on and which one on? That's a 1, I think 1 and.
Yeah, those two would be 4.
1 and 3 are on in the positive, and 2 and 4 are on in the negative.
Okay, 1, 2, 3, 4, right? So this one on and this one on.
But you should always be biasing 2 of them for full wave rectification.
Right.
Mr. Fan, can you do a circuit modification with the CM?
The circuitry on the
Do you have
on the circuit, right?
yeah, do you have the ability to do a circuit on the software? All right, so you're not using software, so I was wondering if you can turn part of the circuit on and off with the CM. Excuse me.
What you're saying, turn the scope on off.
Oh, I was just wondering, because I know, and you know too, when you're using the software, you can do a circuit modification with the CM, turn part of the circuit on or off. So I was wondering if you had that option to turn the diode off and then measure part of that circuit
No,
if it was modified. All right, thank you.
we cannot.
But I think in general, it's a step up, goes from 20 to 25 or whatever it was. And then you cut that in half, and then you have to subtract out the forward biasing of 2 diodes, gets you down to the 11.6.
It's only one diode because the voltage you're measuring is only across one diode. If you were the negative, if you were connected toward the battery side, then there will be 2 diodes. But as it is only across where say positive and negative, if you follow the circuit, you're actually going through only one diode.
Okay, so anyway, you suppose you get around 9 volt or 9.4 something. Let's see, that TV object we pick and set measure the peak DC output voltage. And that's what you get around 9 volt. Okay, and you connect the meter. A meter common connect to the negative. Now they want you to using the DMM. Okay, setting to measure the DC. And you measure across positive, negative. What do you think the voltage you get?
Six 6.7.
Yeah, around. That's easy. So that's why I'm not show you how to do it. You just connect your meter. Okay, set to DC and measure it. Otherwise, the thing is we cannot get through it. Okay, and now you connect the channel 2 this way. Positive to the secondary. Okay. Now I can get one. Positive to a secondary. Okay. Then now you're looking the signal. So they will be full way or halfway.
Shows only half.
That only telling you that the tool is working. I go, okay. That will be halfway rectified. Okay, now the channel 1 2 scope will be displayed like you see. And that will be negative portion. That means the negative right here. Of the waveform show, positive portion. When the diode is to conducting, is voltage drop, LB. Whoever already done, you know which one. Okay. Measure the voltage drop across the tube when it conducting. What do you think, what the values you get? But I think your guy almost done everything on this thing.
9.4.
On the scope screen, measure voltage drop across the tube. Okay. When it conducted. When you measure the voltage across the diode,
0.7.
minor. You know that will be a minor, right? If you're looking in the circuitry here, when the diode, that one you say on, okay? So that means one side will be positive, the other side will be negative, okay? So when you measure that, you will be get a negative minus 0.5, 0.6, or minus 0.7. Okay, so they will be, I don't care that thing, I don't care that one, A or B or C or D, that's okay. Now, they try to do the same thing again, okay? Okay, so if you're looking on the circuitry, on the type, the circuit that you can connect look like that. They will be half-wave diode, capacity input, full wave bridge rectifier without a load. A or B or C, quickly.
Oh, you mean the circuit right there? That's a full wave bridge rectifier.
Yes, I agree. You know that a full wave bridge rectifier. Then what else? A, B, or C?
There's no load at C.
There's no,
The answer will be C.
yeah, right. There's no load on it. And it's a rectifier, bridge rectifier.
They don't have any load resistance.
Right.
Okay, so now they connect it like look like the last one. Okay, and they measure. Clip bottom here, same thing, 20 volt. Okay, peak to peak, 60 hertz. Now they want 60 hertz. Then we can change the generator to the 60 hertz. Okay. And they would still be same thing, okay? Now, let's see what else. Connected into a probe, okay? They will be display the true signal. They will be halfway DC, filter full way DC, unfilter full way. LBOC.
A,
They cannot be A.
No, it's not halfway, because we're only dealing with full wave.
Right.
oh,
ABC.
Would it be C?
Gonna be
Exactly.
C.
Unf-
Exactly.
It's confusing.
Why you think that should be C? The difference between B and C. One they say filter full way.
For
C will be unfilter.
filter, you need a capacitor anyway.
Exactly. If you want to fill it out, you need a capacitor, but we don't have a capacitor. So they have to be answer will be C. And now they want to measure here. We already did it. I don't try to. Now, that's what I need to do. Show you right here. SC1. Okay, so now we add in C1. Okay, adding C1. Still keep the same scope. Okay, when you add C1, okay, the answer in ABCD here, the answer right will be full wave rectifier with the load, resistance, capacitor, input filter at the bridge rectifier, LBOC. That's easy to answer, right?
That's B.
B, that's B.
B. Capacitor input filter at the bridge rectifier output
Yeah, it didn't even have a load resistance.
with a meter. Measure the DC output voltage. The bridge rectifier. What you think?
You got two diodes on and two diodes off. So two diodes are forward bias. So it's either
What
One-
the DC output voltage?
I'm just guessing 1.4.
Ah, come on. How much the voltage without the capacitor?
I don't know, Mr. Pham.
Oh,
peak.
Would it be 10?
Oh,
Yeah.
well, yeah, we couldn't
Okay.
see. We couldn't see the oscilloscope.
okay, now I connect it back. Okay, that one in here. So that's what you can see on the scope.
Capacitor just blocked it.
That's input, right?
Input on the top
Oh, okay.
and output will be a second channel two.
Well, you have your mean at 12 volts.
The answer will be 12 volt. But you know why? Okay, the reason is without the capacitor, the voltage will be a 12 volt here. Okay, full way. However, when you connect a capacitor will be charged up. They charge it up and they not discharge it. So that's why they still keep 12 volt. Okay. Okay, let's see, output,
And that's at the
Yeah.
positive pulse, right?
no pulse. That you can see on the scope, it's a straight line. If you're looking on the measure here, they say, I set the measure mean DC, and they give it you 12 volt. I'm using my scope here. Okay. That one can show measure pitch to pitch. That one measure the frequency. That one I want measure DC. That means DC. They tell me 12 volt.
Hey,
You
Mr.
need to understand, capacitor charge it up, they not discharge.
Hey, Mr. Pham, can I ask you a question regarding the word mean? In this case,
DC. That's a DC using, if they display on the scope.
I was gonna ask though, is mean another word for average?
Now,
RMS.
that's a DC voltage.
Okay, thank you.
Okay, quickly go that one. I don't care that one. Now remove C1, connect to R1, readjust scope, whatever here. We don't care. Output will be unfiltered. That's 74K, doesn't matter. Connect C1. Okay, so now they want to connect with other two. Okay, so we will connect capacitor C1 to R2. You can see I can move that one, connect R1 here. Let's see. R1 to C2. So you need to connect one more here. Okay, to C2.
So that question 17 there, is that B? Is that B as in boy?
Wait a minute.
Okay.
Okay, C2. Now, connect C1 and load resistor R2. Oh, R2. Sorry, not C2. R2 here. Okay, that's correct. R2. Now output and channel 2, unfiltered output of a diode full-wave rectifier across 47K. Filter output LB.
B,
B, correct.
because the capacitor
Right.
block.
Exactly.
Mr. Pham, the capacitor block DC, right?
But the thing is that a filter.
Yeah, right, okay. Filter.
At that scope that on Joe's object and a ripple. Okay. So they say you adjust the scope to see any ripple. And then, let's see. I set auto set measure.
You got to show it to us, Mr. Pham, so we can see
Yeah,
it.
not yet. Okay, now you can see on channel Joe. The signal will be look like. That will be a ripple. Ripple, that means on the top of the DC, you can see that signal.
AC riding on DC.
Right. But that's too small. Okay, compared to DC. So that's why you have to block the DC. Set a scope to AC. Okay. And now they want to measure. If I'm looking on that one, measure pitch to pitch. On the channel 2, they measure 134 millivolt, but that's not a really good measurement for the small signal. With the scope, normally you need to using the cursor. Okay, so I can using the cursor. So you can press the cursor. And source will be channel 2. And the type I change to the voltage. Okay. Then now you can move the cursor on the top. And the second one cursor to the valley. You can read the difference. Delta. They are around 98 millivolt. That's a ripple. Okay. If I put a scope on DC coupling, you cannot see this signal. Now you can see, I can try for you. Scope channel Joe, coupling, I change to DC. Auto set, measure again. You see that? You cannot see that signal. How come? The thing at DC is too high and the ripple is too small. So that's why you cannot see the ripple.
Hey, Mr. Pham, let me ask you something. Did you say this in the past? I don't know if it was you or Ty. When you put your scope on AC coupling, it allows you to see AC. But if you put it on DC coupling, you see both of them, or is it just the opposite?
You see both. However, the DC is too big.
Okay, so on DC coupling, you can see DC and AC?
Exactly.
But on AC, you see only AC?
Exactly.
Okay, thank you.
The thing is right now on that, the DC is big, AC is millivolt. So you cannot see the AC. So in order to see the AC, you must set your scope to AC coupling. Now I set it back to AC coupling. Channel 2, channel to AC coupling. Auto set, measure. Okay, let's see, auto set, measure.
There it is. It's inside the,
Yeah. Oh, man.
maybe move the one signal up and one down.
They already did it. Data AC right here.
Right, right.
You can make it bigger. To measure. You see that?
Yeah,
Otherwise, if you put it on the DC coupling, you cannot see this signal. That is the one I will want to bring it up for you guys. Okay. Okay, so whatever measure here, so they can add in to get a triple. Same thing. If you know how to do it, then you can get everything done. However, in this one, they say CAM15, deactivate. How much the student understand when you say CM, activate, what's going on?
A change was made in the circuit board.
If you're reading, they say CM15 is activated. How much you understand what they're doing?
they set, the LabVolt has internally set itself up to modify the circuit for whatever is coming, whatever you're going to do.
Exactly. That means at this point, LabVolt using the software try to change, for example, 47K to 47O, and they try you to do it over. Okay, and here they can tell you right here, observe toggle on and off, disconnect from circuit, disconnect C1 or source C1. Okay, so that means at this point, you either they disconnect the R2 or they disconnect the C1 or they short the transformer. That means you have to see which can be happen. Okay, A or B or C or D. Okay, so basically, when you measure on this exactly the same, and you can see the output coming out is different, and you can see either what happened here, A or B or C. So the answer will be they try to disconnect C1. That means they remove that one. If they remove that one, when you measure output here, what do you think? There will be no filter. Okay? So you can see that a full wave rectifier. So you know that will be, they're using software to remove C1. However, I just want to let you guys know, when they're using CM, that means they're changing the value inside the circuitry. Try to say you redo again and make sure you can get the right answer. Okay? So that's it. Any question? The thing is, from now on, I will be concentrate on the semiconductor and the transistor. okay? On the AC1, AC2, the students, if still working on that, you get a problem or really slows you down. Text to me, telling me which block, which circuitry you got a problem. I will help you out. We have to need to speed it up, okay? And this matter we're talking about, transistor amplifier. So that's why I will be concentrate on that. So you can see at this time I can improve a lot using my camera. Much better to me. Okay, any question, anything?
Hey, Mr. Pham, if we go slow enough, we can stay with you for 2 years. Okay, thank you, Mr. Pham. Have a good night.
Yeah, the thing is, what I try to help any student really want to learn, really want to be a real technician. Then I guarantee you will be perfect. And maybe next few more years, see you again, you can be engineering. I can, sure. Okay. So, any question for me? Otherwise, good night.
Good night, Mr. Pham.
Yeah, we will see you guys
Night.
tomorrow.
Have a good night.
Good night.